Good morning. I'm sorry that I'm 5 minutes late. I've been having to try and set up all my laptop and whatnot in school and getting all the webinar stuff. I had to go CIT. There we go. Okay, so I'm doing my year 10 lesson. I'm kind of hoping that you guys are going to all be here. Can you just all check that you can all hear me okay? Good morning. That's a good sign. I think that is a good sign. Okay, right. I'm going to try and aim to do the lesson in hopefully less time than what we would have done in class, as since I'm 5 minutes late. But here are my learning objectives. So 10D, last lesson, we boxed off atomic structure, and we were having a look at isotopes, and we were talking about how we can calculate relative atomic mass by looking at the percentage or ratios of the different isotopes for elements. And today we move on to what's called periodicity. This is one of my favorite topics because it's all about my table. And you guys know how much I love my P table. So we're going to be looking at periodicity. Actually means the trends in the periodic table or the patterns. I know that lots of students, in fact, I'm one of them. I remember studying, of course, chemistry when I was in school, and I always needed that translation to words I found a little bit easier. So the word trends is also patterns in my table. So we've got 4 learning objectives today. We've got learning objective number 1 is a knowledge. We're going to recap electronic structures and look at how that links to my periodic table. It's a reminder. I know that we've already done it, but we're just going to go through it again. Next one is understand that the outermost electrons decide properties. Next one is understand noble gases. So I'm now actually dropping into the families of my wonderful table. And the last one is be able to give the number of electrons. Students who aren't sure on what NO dot means, it literally is a short form of the word number. Give the number of electrons, and you'll notice again, I'm shortcutting electron to E minus, and that should be superscript. This little that symbol there should be superscript. I don't really like the fact that it's there. Should be up. Electrons lost or gained. Okay, so let's do my first learning objective. Now, I had someone comment on the notes. And by the way, I do need you guys to give me a bit of feedback. I'm trying to go slowly here so that you guys have time to make your notes in your exercise book. I do realize that it makes it harder for me to judge the pace of a lesson in terms of writing when I haven't got you all in front of me. I am aware of that. I've only actually got 3 people currently watching. That's a bit frustrating, that for me. Kind of hoping that the rest of the class are going to show up at some point, but we will see. Okay, so let's recap our electronic structure. So let's do recap, subtitle, and let's do electronic structure. So this is what we did a few lessons back, and we realized that we can use our beautiful table in order to write out electronic structures for certain, or for anybody up to calcium for GCSE. So this is our end point at for GCSE is calcium. And let's choose somebody, let's do sulfur. So if we're going to work our way through sulfur, you read the periodic table like a book, from top down, left to right. The first row, we've got 2 people. So there's element number 1, there's element number 2. So we've gone across and we've read it and we get the number 2. And then we put a comma. And then we read the next one. So then we go through this line and there are 8. So there is 1, 2, 3, 4, 5, 6, 7, and then 8. So we passed all the way through that line. So there's 8. And then we read across until we hit sulfur. So that's going to be 1, 2, 3, 4, 5, 6. So we've ended there. So our final then electronic configuration, it's all about being able to read this table. So our final configuration for sulfur, if I go back to my notes, so we can go sulfur has a configuration of 2, 8, 6. And it's always nice. Mr. Duncan, Kieran and Vic can't watch because they're now in the music for this year. That's fair enough. I do understand that. I do get it. So it's nice just to check, and I always love that that chemistry has got these checkpoints for each of these kind of questions. And sulfur, of course, sulfur is 16 and 32. And of course, we all know that the number of electrons is equal to the number of protons, which is the atomic number here. This is the atomic number, and this is the number of protons, but also the number of electrons, so the total number. Well, if you just sum those up, we get to the number 16. So it's nice just to confirm it and have that, oh, right, that's really nice that I can actually check to see whether I'm correct, which is a really lovely thing to do. I don't think I need to do any more than that. So we can kind of tick that off and say, I'm pretty sure that everyone in our class can do this. So, okay, we now come to our understanding that the outermost electrons decide the properties. And also technically 2 people watching because I'm not in this class. Okay, thanks Laura for letting me know. Okay, so let's do our electrons and our outermost. So what we now realize is we go back to our periodic table, and I'll erase all of my data. So I get to do a little bit of a history lesson now, because when chemistry was first born, and students often say, how can chemistry be born? Well, the subject was kind of created by a group of people called alchemists. And the alchemists were kind of like, it's always nice to do kind of the googly bit of this. So if I do alchemists, and alchemists are kind of these people in dark laboratories hundreds of years ago. And these guys really gave birth to the subject of chemistry. And they were the ones that started playing with things and seeing how they behaved. And they were the first people to start grouping substances in terms of their chemical properties. And some of those elements they were grouping still are seen on our kind of periodic table now. So we've got things like mercury and gold. Now these 2 were known by the alchemists, and they were put in a class together. They were put in a group of unreactive metals. So if we go element groups, and you'll notice I'm using this term, element groups, and I need to be very careful when I use this word, because this is the word that we now use for the groups of our periodic table, our columns, and we know this. A group on the periodic table, a group is a column. A group equals a column. Is that how you spell column? A group equals a column. So we can, and this still stands today because there's a really important thing here, because the word group also means, in this case, groups. I'll put it into words. Groups share similar properties. Now the alchemists started doing this, they were kind of the first people to do this. And the groups, they didn't have a huge number of groups the way that the periodic table does today, but they certainly had groups. And for example, they had metals and non-metals. So they had one group here of metals, and then they had another group of non-metals, substances that were clearly not metallic. Then they started subdividing them. They then realized that there were some metals that were unreactive. And these were things like gold, AU, Aurus, but I'll put gold, silver, platinum, AG. You know what? I've done the symbol. I hate being inconsistent. AG, silver. Then we've got platinum, PT, platinum, mercury. And they lumped these together. Platinum, mercury, Hg. They put all these together as the unreactive metals. And now, if we look at them on the modern periodic table, we find them all in a very similar place. Silver, gold, mercury, platinum. They're all in this central column, in this middle block here. And this block is called the transition metal block. Hi Ben, glad you made it. Got 4 people now. So this is now the transition metal block. Now, of course, the alchemists were just grouping them on their properties and didn't realize the significance of what they were doing. But it now, of course, makes an awful lot more sense, because we can actually now put them into our table and see that they all of the people in the middle are deemed unreactive metals. Unreactive metals. So why is that? So why did this middle block, this transition metal block, and we can do a little note on the transition metals now, because today's lesson is all about the trends in my table. So I'm deciding how I want to do this in terms of my notes. So I'll do it underneath here. So the first group that we're going to put into our notes is the transition metals. Transition metals. And we pick up this, and as I said, this comes from history. I tend to start here because of the alchemists and the history that is behind it, which is rather lovely. So we realize that the transition metal block, it's quite nice to draw a little table and realize that where it is. I hope you will see what I've done there. Look at that. So it's this section here in the middle. This section here, they are unreactive metals. They are unreactive metals. Why? All have 2 electrons in outer energy level. Notice how I switch from the word shell to energy level. All have 2 electrons in outer energy level. Remember, I do love the word shell. I do, but you shouldn't. In an exam, you have to be really careful. You must say the word energy level. So I tend to prefer you guys to write down energy level and tack on shell at the end. So we now discovered the explanation. It took us a couple of thousand years to do it, but we discovered the reasoning behind the unreactive nature of these metals all ties in to the number of electrons in the outer energy level. Okay, so let's now go back to my table and see if we can pick up any other groups of real significance. And we do come across this family. And I think this is part of my learning objectives. Let's have a look at my learning objectives. So, yeah. So we're now realizing, thanks to a bit of a history lesson with alchemists, realizing that we were grouping these metals and substances, and they were putting them in these families of reactive and unreactive, and they're now realizing that it's the outer electrons that are going to be deciding this. So we can kind of tick that one off. We now drop into the next family, our noble gases. Now, we can run through our noble gases. Let's have a look at some of them. So you can put a little subheading of noble gases. Now, can I just say that the noble gases have a beautiful, beautiful story behind their discovery and their addition and their addition to the periodic table. And the guy who found all of them is a guy called Ramsay. And you know what? It's really sad because, you know, as a scientist, you always wanted to discover something in order to be able to be remembered, and you want to make your mark. And Ramsay discovered almost all of the noble gases. In fact, by the way, he did actually discover all of them, apart from the one that has now been recently made. But Ramsay discovered all the others. And the reason why he discovered them and the story behind it is because the table had been built and these guys weren't there. The whole group was missing as we started, and the reason why is because they're very hard to find. The noble gases are very unreactive, and they were some of the last elements to be discovered. Now I need to give you another word for unreactive here, and I need to give you it. I'm going to put / inert, The reason why is because that comes up at GCSE really more than the word unreactive, which is frustrating for me when they mean exactly the same thing, but it's important that I mention this word. These two mean exactly the same thing. Inert and unreactive, they are synonyms of each other. They mean exactly the same thing. So these elements were the last to be discovered because the problem is if something can't react with anything, then it's very difficult to actually isolate. Not just isolate, but it's difficult to even know that it's there. Now, if we look at our column, we've got helium. I think everyone here recognizes helium. I'll actually write the four names. Helium, neon, from neon signs. Helium, of course, from balloons. Argon, krypton, and radon. So we've got 5 unreactive gases. Let's just check on that one. Helium, neon, argon, krypton. Oh, I missed xenon. I knew I'd missed somebody out. Krypton, xenon. That's really mean. Xenon and argon and radon. Oh, no, argon. No. Radon. Because it's the radioactive one. Yeah, so here are our noble gases. And the first one of these to be discovered was argon. Argon was the first to be discovered. And it was discovered because it is in the air we breathe. It only is a tiny percentage. It's very, very small. Less than 1%. It's like 0.89 or something like that. I'm tempted to check that. In fact, I will. Let's just look up. I know that it's less than 1%. Let's go argon in air. Argon. Oh, I've missed. It wouldn't really actually help if I spelled that correctly. Argon. It's on a capital G. Amazing. Argon. Let's look at its percentage. I'm surprised that nobody's helped me out on the chat yet. Oh, there we go. Less than 1%, but 0.934. There we go. So I'm just gonna do 0.9%. So it's in the air that we breathe. Now this, have you seen the Noble Gases song? No, I can't say I have. Oh no, it's gonna be a joke, isn't it? It's gonna be something to do with they're all gone. Anyway, so argon was the first to be discovered. Now the reason being is because it was in the air. So what they did, the method that Ramsay used, the method that Ramsay used, should look him up. It's a great story. He took a sample of air. Now, of course, he knew at this point, we had already identified that the air contained nitrogen gas at 78%, and it also contained oxygen gas at 21%. Now, the problem is that they actually thought that it was actually that. They thought that they also knew that there'd be water vapor in the air and a small amount of carbon dioxide. In fact, we can do that. Let's do H2O, gas, has to be gas, and also CO2. That was pretty much what they thought the air was. Now, you can remove each of these gases chemically. So if you want to remove all the nitrogen and oxygen, first thing you do is you're going to run electricity through this sample. Use lightning. I'm going to write lightning down. In reality, they use sparks. And what will happen is the nitrogen and oxygen will react together to form nitrogen dioxide gas. We can even do the equation for this. N2 plus O2 goes to NO. In fact, I'll do NO2 because that's GCSE really. And we can balance for that. 2 nitrogens, 1 nitrogen. I need to double it. Right, 2 nitrogens, 2 nitrogens, 2 oxygens, 4 oxygens, and I'm done. So we can remove these two gases very easily. Next, we can remove water. You can remove water with a drying agent. We're going to use a drying agent, or by the way, its actual name is called a desiccant. Desiccant. And otherwise, I'll put underneath that drying agent. If anybody's wondering of an identity of a drying agent, the classical one is calcium chloride. So if you add calcium chloride solid just into the container, just kind of down here, it'll remove all of the water. Next, we can remove the carbon dioxide. We can remove the carbon dioxide by putting the air through something like lime water. There is actually also an agent that can do this. We can remove using lime water. Using lime water. I can give you the equation for that as well if you like, which is calcium hydroxide plus carbon dioxide, CO2, goes to calcium carbonate and water. And we can then remove these because, of course, the gas is now gone. That one was aqueous. This, of course, is a solid, and that, of course, is a liquid, so we just pull these out. Now, at the end of all of this, and I know this seems awfully tiresome that I'm doing this, but there's great chemistry in here. There's great chemistry in all of this. And after all of this process that Ramsay did, he discovered there was still a gas present. In his jar, after all of this process, after everything had been removed, there was still a tiny amount of gas left over. If you imagine the jar being full of particles, and I said, here's the nitrogen, the nitrogens are all yellow. These are the yellow ones. Here are the oxygens. Here's the carbon dioxide. Here's the carbon dioxide. And those, so as we remove these, so we removed the nitrogen and oxygen by reacting them together. We removed the carbon dioxide and the water vapor. And as Ramsay did this, he then realized, that's frustrating, isn't it? He then realized something very, very strange, which he did not expect. I know I've just removed one. And that was the fact that there was still a gas there. And that was very special. He was like, there's still a gas. And he had no idea what this gas was. So he tried to test it. It didn't do anything. So its chemistry was incredibly unreactive. It wouldn't react with anything. So he looked at it using light. It's called spectroscopy. He used what's called visible light. Visible light spectroscopy. And I can show you what he got, which is really cool. So he got argon spectrum. It's such a great story. And that's what he saw. Let's see if I can find the correct picture. I'm hoping that this is going to work. Let's try that one. Come on. Give me what I want. There we go. It's actually really, that's better. And this is what he saw. He saw this picture here. I don't know if you can see my little cursor moving around. I don't know if you can. I can probably actually clip that and then have a look at it like this. So what he saw was this, which was, for him, he was like, okay, so I definitely know. Tusk shakes head. Tusk. Shakes head. So that's what he saw. And so he knew there was definitely something in there. He hadn't made a mistake. It had a signature. And he called it argon. And the word argon comes from the word stranger. Argon, the stranger. So if we go argon, the stranger. Because I think if you look up the word argon, hidden, there it is. It's just nice to look at where the words come from And it's got, as I said, it's really lovely to see those derivative names. Let's see if I can find it. Helium was named after Helios, which means, of course, sun, because they realized that when they discovered helium, its spectrum was actually in the spectrum they saw from the sun. So they realized the sun had helium in it. I'm still trying to find, there we go, stranger. So then, there's stranger. Anyway, so let's go back to this. So now he then went on an enormous task. He spent the rest of his life trying to track down all the other noble gases. Helium was discovered by him when somebody had reported that when you had radioactive rocks, that they were spitting out a gas that they didn't recognize. So he went and investigated and discovered helium. All the rest have got similar stories behind their discovery by Ramsay, and I just think they're all really, really lovely. So the question is, Ramsay created this entire group and he added it to the table. Helios also came from the Greek god of sun, the word Helios. Yes, that's correct. Hold on, chat. So he added this entire group to the table, but he then had to go about trying to figure out why they were unreactive. And then we can now say, can you just put a little subtitle of why noble? And I love the word noble here because I'm using this word in two ways. One, because of the gases having that family name, the group name, but also because the word noble means royalty. So why noble? Why unreactive? Why don't they react with anybody else? And it turns out that it's all about their electrons in their outer shell. So let's have a look at what this looks like. So helium. Helium only has one shell, and it has 2 electrons in it. So we realized very quickly that helium's outer energy level, I'm just going to put EL now, energy level, was full. If you look at the next one, helium neon, 2 in the first and 8 in the second. And we realized that once again, it had a full outer energy level. Helium, neon, argon. Now, students of mine will know something here, and I've got to be careful. Year 10s, I've taught you too much. Because what I now need you to recognize is that if in an exam they ask you why argon is unreactive, you're going to say because their outer energy levels are full. If you want the more correct answer, the A-level answer would be because they have a stable electronic configuration. At GCSE, configuration. At GCSE, we say full outer energy levels. Full outer energy levels. So, they have a full shell, so they don't react, right? That is absolutely correct, Lara. Now, at this point, Lara, I love that you've made that jump before I did it. It's really nice, that. Now, what this means is you're starting to understand or question what a reaction is. And this is really my next bit. So we can now go back to my learning objectives and just tick off, we now understand that all noble gases are inert and they all have full outer energy levels. We all know this, they're all full outer energy levels. So they are inert, unreactive. Well, hang on a minute. If we're saying this, it means that we're now saying that chemical reactions You have been learning about these now, folks. Chemical reactions. You've been learning about these now for at least 4 years. No, okay, that's not true, is it? 3 and a bit. 3 and a bit years. And at no point does anyone ask, why do they do this? Because the answer is in this lesson. It is, atoms want to be noble. So you can make this bullet point. All atoms want a full outer energy level. I'm just going to put EL. All atoms want a full outer shell because everybody wants to be noble. Everyone wants to be royalty, wants to be noble. Now, if you want the A-level bit, it is that all atoms want a stable. By the way, you're allowed to write this one in. I'd like to think that you guys see what I'm teaching. I know that there are lots of people who switch off when I mention A-level in a GCSE lesson, but in reality, I'd like you to think that you realize that I'm not just teaching you GCSE, I'm just teaching you good chemistry. That is all. And so that's always my prerogative. I want to teach good chemistry, and this is where this goes. So all atoms want a stable electronic configuration. GCSE, A-level. My year 10s will also understand the reasoning behind that a little bit better than perhaps others. So, if everybody wants to be full, so, ... This is exciting, isn't it? So, if everybody wants to be full, then what are the atoms going to do? Let's choose a couple of people. Let's choose sodium, Na, element number 11. It's number 11 because it has 11 protons, and it has also got 11 electrons. Let's look at its shells. I don't want to take that away from you guys quite yet. Here's sodium. 2, 8, 1. Now it wants, how do all atoms get a stable electron configuration? Are they going to share? Wait, Mr. Denkin, what does EL mean? It means energy level, Shan. Zach, what a great question that is. And the answer is, they're going to either. Let's look at sodium. They could lose. Now, sodium has one electron in outer energy level. Outer energy level. One electron. How do you get full? How could sodium get full? What are its two options? It can either lose one electron or gain 7. I'm going to put it to the classroom. Guys, which one do you think it's going to do and why? This is where I need the, I'm going to do something really funny now. I really want the countdown 30-second timer sound effect. That would be awesome. Love that. Let's see if we can find it. And then I'll put it on. This is only for when I ask you guys questions. Lose, because it's easier. Zach, spot on. That's the answer. It's going to lose. Zach, why is it easier? Why do you think it's easier? And by the way, this isn't chemistry. It's just common sense. That's the right answer. Thanks, Zach. Commendation to you, Zach. Remember to come and ask me and I'll give it to you. I'm well impressed. Well done. It's simply because it's a smaller number. To gain 7 would be crazy, but to lose 1, that's doable. So sodium is going to lose the 1 electron and not gain it. because that's much easier. So it's going to lose 1 electron. Let's now have a look. Let's highlight that on my beautiful table. I love my table. Just makes me happy. So let's just find sodium. Do you know what? I'm going to clean the table off entirely. I'm going to clean it up. There we go. There we go. And I'm going to highlight sodium. There's sodium there. That's a bit dark, isn't it? Let's try this again. Let's see if I can alter my color and make it a bit lighter. So sodium, it's going to lose 1. Right, let's have a look at potassium. Potassium is element number 19. It has 19 protons. He didn't see my answer. Shan, where's your answer? All well. Huh? I can't see your answer. No, I can't. Wait a minute. I can't see your answer. Anyway, so potassium has 19 protons. It's element number 19. And it also has 19 electrons. Let's look at what that looks like. It's got 4 shells. How do I know it has 4 shells? Because my table tells me so. 1, 2, 3, 4. It's in row number 4. It's got 4 shells. And I can say there are 2 electrons here, 8 electrons here, 8 electrons here, and 1 electron in its outer. No, because Laura's answer was after Zach's. That's why you didn't see it. Okay. I'm with you. Okay, Laura, what's potassium going to do? Oh, this is where I need my countdown clock. I've got it. Hang on a minute. I've got it. Oh, it's amazing. Right, Laura, you said lose an electron. Can you give me I know that your answer is correct. Well done. Can you just write a number in that, though? I know that an means singular, but they always want a number. Yep. So, same thing with Zach. You've got to include the number. It's going to lose 1 electron. Cool. So, let's just check where it lives on my table. And I'd love to think that you guys will suddenly go, it's below sodium. It's doing the same thing that sodium is doing. Let's look at lithium. Lithium. Nice one. Number 4. Lithium. Element number 3. Let's look at its shells. It has 2 in the first shell and 1 in the second. How many is lithium going to lose? 1. All 3 of these elements do the same thing with their electrons. And look where they live. They all live in the same group. Because your electrons decide your behavior. And they all have 1 electron in their outermost energy level. They've all got 1 electron to lose. Let's now flip sides. We've just been doing metals. Let's flip over. Let's look at another family. So we've just been looking at a metal family. Let's look at another family. Let's look at group 7. Group 7. This is one, by the way, does that mean that the next column loses 2? Yes, Shan. Oh my God, you now realize why. If you teach this properly, I don't have to teach it because I show you one thing and you get it. That's exactly it. Lara, Shan, you've got it. Okay, so you guys have already done group 2 for me. Thanks very much. So group 2 are going to lose 2 because 2 is less than 6. Thanks, Lara. The chat's perfect. So here's a question for you then, Shan. Impress me. And Lara, what's going to happen with group 7? I now need my countdown clock again. Where's my countdown clock? amazing. Thanks, guys. That was perfectly timed with the clock as well. That was great. They're not going to lose 7, Shan. I love that, Zach. Steal. Yes, well done. Lara, well done. They're gonna gain. So fluorine, 2 shells. First shell, 2 electrons. Next shell, 7 electrons. It needs to be full. It wants to be noble. How does it do that? It wants to get to the number 8. What it's going to do is it's going to steal 1. It's going to gain 1 electron. It's going to gain because it's easier to gain 1 than lose 7. Let's look at chlorine. 3 shells. How do I know it's got 3 shells? Because it's in row 3. There's chlorine. Let's look at bromine. 4 shells. Iodine, 5 shells. So we can now go, let's look at bromine. 4 shells. Iodine, 1, 2, 3, 4, 5. And all of them have 7 electrons in their outermost energy level. They all have 7. What that means is every single one of them is going to do the same thing. They're going to gain 1 electron to become full. So will group 7 react with group 1 to get 1 electron? Lara, you're doing such wonderful chemistry. And I love it. You're realizing you're literally making all of these connections now yourself, which is wonderful. Yes, of course they do. Do you want to see what happens? So at this point, if I was in lesson, at this point, I would be showing you guys a video of the reaction of sodium and chlorine. In fact, heck, I wouldn't even be showing you the video. I'd be doing it. I'd get some sodium metal. So sodium metal, which is, by the way, sodium is a silver shiny metal. So I'd get a piece of sodium, not this big, by the way, that would be mental. Silver shiny metal of sodium. I'd get some of this. And then I'd get some nasty chlorine gas. Chlorine gas is a pale yellow greenish kind of gas. So here's my chlorine gas. I'd have that in a jar, just so you know. I'd have that in a jar like that. And then what I'd do is I'd put the jar on top of the sodium and I'd light it on fire. And what you get is you get a cloud of white smoke and a beautiful flame. And what you make is sodium chloride, which you guys all put on your fish and chips. Let's look at what happens in terms of electrons. So the sodium atom had 1 electron. I'm going to draw all the shells. Sodium, first shell, 2 electrons. Second shell, oh, it's getting big. There we go. Second shell, it's got 8, it's full. And then its third shell, oh, sorry, it wasn't great, did my best. Third shell got 1 in it. There's a sodium atom. Here's now chlorine atom. Chlorine on the other side has got 2. It's got, do you know what? I'm usually better at doing circles than this. That was a bit better. 2, 8, 7. Right. So when these 2 atoms now collide, and you know what? I'm suddenly realizing I've done a bad thing here. I should have done these guys as dots so you can tell whose is whose. So let's do that. And what's going to happen? Mr. Duncan loves fire. I do. If I have a chance to set fire to something, I will. It's going to swap over. So metals, and this is one of the greatest and amazing things to be able to sum up. Metals lose electrons, and the non-metals gain them. The non-metals gain electrons. And they swap, and once they've swapped, they now stick together. Now, that is for another lesson, just so you know. Today's lesson is now done. We are finished. Give the number of electrons lost and gained. You guys figure that out on your own. Group 1 will lose 1. Group 2 will lose 2. Group 7 will gain 1 and the noble gases won't do anything at all. I'm going to ask you one more question before I end my lesson. So, I might ask a couple actually. Let's just do a little bit of just assessment. Okay. Okay, folks, here's my question to you. How many electrons will oxygen lose or gain? Which one will it do? Will it lose or gain, and how many? Yeah, winner! Lara, well done. Oxygen is going to gain 2. Yeah, look at this. I love that fact that it's now all appearing on the chat. Gain 2, gain 2, gain 2. Guys, great job. Really pleased. So oxygen is going to gain 2. Okay, harder one. What about gallium? Go. Yeah, look at that. Guys, well done, Shanley. Look at that. Everyone's got it. Ben's got it, everyone. So I chose gallium because, of course, you guys wouldn't know gallium at all. Definitely wouldn't know it. But what you realize is it all comes down to my table. It is in group 3. It is in group 3. What that means is on its outer energy level, there are 3 electrons. And it needs to become full. The choices it has are gain 5 electrons or lose 3. Guys, I am so impressed with you all today. You have done a great job. And that brings my lesson to a close. If you guys look at the learning objectives that every single one of you can now do. And I think that's really lovely. Let's just switch back to camera. Hey guys, thanks so much for coming along today. I will continue to do our lessons via webinar as long as the school is closed. I will always do this. I hate the idea of not being able to teach you guys. Because the 4th, but what about number 4? Do you know what, Lara? Yes, well done in terms of charges. You're absolutely correct, Lara. If a metal loses an electron, it means it has 1 more proton than it does electrons. So the whole atom now becomes an ion, which is positive. And the non-metals are going to gain electrons, so they're going to have more electrons than protons, so they become negative. And that is another lesson. That is, in fact, the next lesson in the sequence. Atoms becoming ions. And so don't worry. The next one that someone has asked is what about group 4? Group 4 is a nightmare. So group 4 can, in fact, do either. They can either lose 4, gain 4, but there's one other option. There is another option, which is instead of losing and gaining, and trying to lose 4 electrons is tough, but trying to gain 4 is just as hard. So what they do instead is they share. So we'll come again. That's for another lesson, guys. And I could spend the entire day now just teaching you guys over the webinar, and I don't want to do that because you guys, it's meant to be an hour slot, so let's stick with that. But guys, it's been awesome to see you. Thank you so much for coming. Shan, yes, I am indeed in school. I will see you guys for our next webinar, or either that or I will see you in school. Have a great day, guys. I hope you enjoyed the lesson. See you soon. Bye.
I've written